Hello, and welcome to Lecture 23 on the topic of momentum and impulse, and specifically linear momentum and linear impulse for that matter. And linear just means momentum in a line, such as the x, y, or z directions. Okay, this is going to cover sections 9.1 and 9.3. We'll get to section 9.2 later. And since this is our introduction to the chapter and the very idea of momentum, we should define what is momentum. Why are we talking about it? Why do we care? Because so far we have the kinematics, so displacement, velocity, and acceleration. We've got the idea of work as a form of creating energy from a force. And then we have certain types of energies, kinetic energy, potential energy. And we also have mass for that matter, which is inertia. But why momentum? Why do we need another physical quantity? Okay? Well, it's been used by physicists for a long time, and so it definitely has some historical significance there. And also, it is a conserved quantity. And that's really the main reason we care. All right? And we'll get to that later in the chapter. For now, let's just introduce it and tie it in with stuff we've seen before, like forces and acceleration. Okay? But let's define momentum. It is a vector quantity. That's important, right? So it has direction as well as magnitude. All right? And it's equal to simply mass times velocity. All right? So mass multiplied by velocity is momentum. Unlike inertia, and remember for linear inertia, it's just kilograms, right? Inertia is a property of matter, it's mass, okay? Only moving objects or particles have momentum. And I bring that up because a lot of times in everyday language, we kind of interchange the words momentum and inertia, and that's fine, right? But for scientific language, for physics, inertia has units of kilogram, momentum definitely doesn't because it's mass, which is kilograms, times velocity. So the units of momentum would be kilograms meters per second, although I will usually express it a slightly different way, okay? Unlike kinetic energy, another kind of natural comparison, especially considering that kinetic energy is composed of the same units, that is mass and velocity, but in a different combination, because velocity is squared, and of course kinetic energy has the 1/2 in front. But unlike kinetic energy, momentum is a vector. That's another important difference between the two, besides them just having different units and different quantities, is momentum has direction, okay? It is not a scalar, all right? Or of course kinetic energy is a scalar. And momentum is also known as translational momentum. So we see linear momentum, that refers to the fact that it's in a line. Translation refers to the fact that it's x, y, and z displacement, okay? This is in contrast to something called angular displacement and angular momentum, which we'll talk about later. And when someone says momentum, they mean translational momentum, because they'll specify if it's the other type, okay? So there we go. Either linear momentum, just plain momentum, or translational momentum, they all mean the same thing. Okay. So there's one other key term here, one other unit we're going to see, or one other variable we're going to see in the equations, and that's impulse. So what is impulse? Well, impulse is just equal to change in momentum. Okay, it is also a vector. P here, by the way, is momentum. The variable P is used for momentum. Okay, I know the word doesn't start with P, but P is used for momentum. Usually lowercase to distinguish it from power, which is usually uppercase P. But regardless, they both are P's, and it's usually clear by the context of the problem which we're talking about. But momentum is represented by the letter P, and impulse is just a vector equal to that change, okay? Impulse, besides being equal to a change in momentum, is force integrated over time, right? So if you apply a force for a certain amount of time, let's say I apply a force for 1 second, and I want to know the effect of that force applied over that 1 second, then I could measure that total effect, even if the force was non-constant, by finding the impulse, okay? And that's kind of that's the way it gets used. I mean, so you give something an impulse, it's like giving it a push, right? Well, that's a force multiplied by time, isn't it? And that's in contrast to work, which is force multiplied by distance, okay? So impulse is not energy, impulse is momentum, just like work is energy, right? Okay? All right. Lastly, it is just a change in momentum, just to highlight that, okay? It is, by definition, delta P, a change in momentum. And so it's kind of interesting to have a separate name for something that's a change. We don't call, say, a change in acceleration, delta A, we don't call it by a special name. The closest comparison is the idea of position and displacement, because position is, like just a coordinate. A change in position is a displacement. And so there's a unique name for that change. Likewise for impulse. Although that's not the reason there's a unique name for impulse. It's more to do with the fact that it has that relationship to force, and it has a particular meaning, a connotation. It's the impulse. Okay, but let's see what how it shows up in our equations, and let's move on down to key formulas. All right, so here we go. Our first formula is just the definition of momentum. We see it's a vector. We see it's equal to mass times velocity. As a vector, it must always be parallel to velocity. Its units are kilogram meters per second. but I will always write it as Newton seconds, okay? Why Newton seconds? I just think it's clearer. It clearly shows that it's force times time. That momentum is force multiplied by time, okay? But it's also, of course, mass multiplied by velocity. So, it's all kind of how you think about it. And as far as the idea of momentum being force times time, look at this equation. Well, this shows it, right? If I multiply both sides by dt, then I would clearly have some time multiplied by a force is the change momentum. But more importantly, you know what this equation is? It's Newton's second law, all right? And we would say it's Newton's second law in momentum form, okay? Because up to this point, we saw Newton's second law as F equals ma. That would be, and we even call it the law of acceleration. So that would be Newton's second law in acceleration form, all right? And in fact, when Newton first published his 3 laws of motion, he expressed it in terms of momentum, all right? Which was more the unit of the day as opposed to acceleration, which has been more of a modern way of thinking about motion that is kind of developed in the last 500 years, okay? But regardless, we have that force is the first derivative of momentum with respect to time, all right? That's what force is, okay? And let's go ahead and show that this is equal to F equals ma, the more familiar expression, all right? So we could then rewrite momentum as mv, pull the m out of the derivative, and this is, of course, assuming that the mass is constant, which is not the case for some systems like rockets where they use up their fuel, but we're not going to concern ourselves with those types of systems. So mass is assumed to be constant. So then we're just left with dv over dt, which of course is just the first time derivative of velocity, which is acceleration. Okay? So then we see that these 2 ways of expressing Newton's second law are consistent with one another. All right, now on to impulse. All right, well, here we have it, impulse, represented by the letter J, to be consistent with the idea of using letters that don't match the first letter of the expression. Now, you might also see impulse as a vector with as I. I think that's too confusing because I really is used for the moment of inertia. I prefer using J for impulse. All right, and so we can see what it is it's the integration of force with respect to time. But that makes sense because impulse is, after all, a change in momentum. Well, then if I was to say multiply both sides of the equation up here, then I would have F dt equals dp. If I integrate both those sides, then this right here is impulse. See? All right. So that's how we can deal with a non-constant force. Of course, if it is a constant force with respect to time, then it's just force times time, right? So if force is constant over time, then impulse just becomes F multiplied by t, which is fine, right? We're used to integrals just going away in that case, right? If the function or if the variable is not a function of what's being integrated, no problem there. But if it is, then we totally are well equipped to deal with it with calculus. All right? So there we have impulse. Our last expression here is dealing with a particular situation where we have many collisions, and collisions are a real common type of problem that are suited to momentum and the study of momentum. But these are collisions of tiny little particles, like the particles that compose air or water. So this is usually some sort of fluid interaction. And so the n here is the number of particles changing momentum. And the idea is that their change of momentum is going to exert a force on whatever is forcing them to change momentum. Maybe it's water hitting a wall and exerting a force on a wall. Maybe it's water hitting a water wheel and exerting a force on that water wheel, thus turning the wheel. All right, maybe it's wind blowing against the side of a building and actually pushing on that building. Whatever it may be, we think of n as the number of particles. But then we're going to get rid of the n because then we're going to rewrite momentum as m times delta v. All right, and this is average, by the way. Then that's what this denotes here. Though it's the subscript avg and the bar above the f, 2 alternative ways of denoting average. That's why we're seeing deltas and not instantaneous changes. But then let's look at this n times m. Because since these are individual particles, each one has a certain mass, an average mass maybe, then the n times m becomes delta m. And then the delta m over delta t is our mass flow rate, kilograms per second. That's how much of that fluid composed of many individual particles is hitting an object per unit time. All right, so this is applicable to fluid collisions like rain, water, or wind. All right, so let's look at our examples. And really this being a very introductory lecture here on the chapter, since we're just defining momentum and impulse. The examples here aren't particularly in depth. We'll save those for later in the chapter. Let's just lay down the basics. Okay? So, practice. 3 types. Type 1, 2, and 3. Type 1 problems are simple problems that just involve using the definition of momentum. Type 2 are problems that involve using the definition of impulse, okay? And sometimes the integration of time-dependent forces, okay? And so they might involve calculus, they might not. Type 3, problems that involve a fluid impacting a solid surface. I'll be using that final equation and expression and exacting a force on that surface via the change in momentum of the fluid. All right, so let's do a very simple one to get started. Example 1. A 2.5 kilogram stone is released from rest and falls towards the earth with negligible drag. Right, so no drag to worry about. What is the stone's momentum after 7.5 seconds? All right, so we're just going to use free fall to find v. All right, so we'll just do a little bit of free fall background here. We find then that the velocity after falling for this long is 73.5 meters per second. And so then it's just simply a matter of multiplying by mass to get our momentum p. And there we go. And we're denoting it as a vector downward. All right, we could have also defined it as negative j hat, but here we're just going to say it's downward. So it definitely has magnitude and direction. And there's its magnitude, 184 newton seconds. Okay, straightforward. Let's do another one, which is easy once you see what it's asking, but this is sometimes a tricky question to interpret. So at time t equals 0, a ball is stuck at ground level, or struck, and sent over level ground. So this is projectile motion, the type where it's level ground projectile motion. You end at the height you started at, okay? So the momentum p versus t graph during flight is shown. It's a parabola, right? A lot of things with projectile motion are parabolas. The y is a function of x is a parabola. Y position is a function of time is a parabola. And here we're seeing momentum as a function of time is also a parabola. That makes sense because we have the constant acceleration and we naturally get those squared terms, okay? And we're told that P naught is 6 newton seconds and P1 is 4 newton seconds, all right? And at what initial angle must the ball have been launched? Wait, right? Were we given enough information here? We actually were, fascinatingly enough. And we weren't given the mass, we don't need the mass, but check it out. P naught, right? That is the initial momentum value. The naught here definitely denotes initial, and it's 6. That is the biggest momentum value as well, because after that it falls down. It falls down to a minimum value, P1, of 4, okay? So that's interesting. The momentum starts at some maximum value and then it ends at some minimum value. Well, think about projectile motion. When is the velocity minimum? At the top of the projectile's trajectory. Well, if the velocity is minimum and the mass is unchanging, that means at the top of the trajectory, the momentum must also be a minimum. That means that this represents the top of the trajectory, the momentum at the top of the trajectory. If that's the momentum at the top of the trajectory, then we know that the velocity must be entirely horizontal, which means that this is just the x component of momentum, because remember, momentum is a vector, right? And from there, it all falls together, right? Here's just a picture of the projectile motion, all right? Basically, y is a function of x graph, all right, with y and x, okay? Here we have our initial velocity broken into its vertical and horizontal components, and then we have the velocity at the top, which is just equal to the initial horizontal component of velocity because there's no acceleration in the horizontal direction, so that component of velocity is unchanging. And then I'm showing that that's v1 to be consistent with the notation in the graph, right? So in other words, p1 just equals mv1, okay? And so then we're going to have cosine, because this is what we're asked for. We're asked for the launch angle, theta. Okay, well, cosine of theta, which is going to be adjacent over hypotenuse, is going to be v naught x over v naught. Okay, well, that's going to be v1 over v naught, isn't it? Right? Okay, and then we know that v1 is just p1 over m, just using the definition of momentum, and v naught is p naught over m. The m's cancel out, why they weren't provided. All right, and then it's simply a matter of plugging in our 4 over 6, doing an inverse cosine to solve for theta, and there we go. There's our launch angle. So it's pretty neat, very simple, but it's interpreting the graph and seeing that you do in fact have enough information. Okay. All right, let's move on to another type of problem, those that involve impulse. A force is provided to a golf ball at rest with a mass of 140 grams. Through contact of the golf club, the force is constant, constant, that means no integration, and has a magnitude of 910 newtons, yet the force is provided for 45 milliseconds, so short time. That's typical of situations that are well suited to momentum. All right, how much does the momentum of the ball change, and how fast is the golf ball traveling after the force is applied? How much kinetic energy does the ball gain? All right, so simple questions, but kind of tying together a lot of ideas. Okay, so we're going to find the impulse. Impulse is force multiplied by delta t as long as force is constant, which it is here. It's also equal to delta p by definition. That's always true, whether or not the force is constant. All right, so here we take our 900 Newton force multiplied by 45 milliseconds, which is 45 times 10 to the negative 3 seconds. All right, and so then we know that our change of momentum then is just going to be this result here, which is 41 Newton seconds. All right, so there we go. We found our change of momentum because we found our impulse, and those are the same thing. Okay, and then in part B, how fast is the golf ball going? Okay, well, my change of momentum is P final minus P initial. P initial is 0. All right, so that means that my change of momentum, my 41 Newton seconds, is just equal to the mass of the ball times the final velocity. I know the mass of the ball to be 141 or 140 grams, so that I can just solve for V final, as just 41 over 0.14, and there we go, 293 meters per second. A respectable speed, okay? All right, and then part C, well, now that we have our velocity and we have our mass, this one is very much plug and chug. We just plug in our mass, we plug in the velocity we solved for in part B, and there we go. Our kinetic energy is 6,000 joules. All right? Okay, good. Just tying ideas together. Hopefully simple equations, but good to see how they're used. Okay, now let's do one that does involve integration. Still not terribly complex, but let's see what it looks like. So a time-dependent force given here, so t squared minus t cubed plus 14t plus 4, all in units of newtons, is exerted on an 814 gram rock over a duration of 4 seconds. So a much longer time, right? If the initial momentum of the rock was 0, which means its initial velocity was 0, then what is its final velocity? Okay, all right, let's do it. Okay, so the first thing we're going to do is we're going to set up impulse, right, with the integral definition of it. Okay, we're going to be integrating as a definite integral from 0 to 4 seconds because that's the entire time that the force is applied. We plug in our time-dependent force equation right in here, and then we just go ahead and integrate it. Here I'm just doing all the rules of antiderivatives for polynomials. So for example, my t squared becomes 1 over 3 times t cubed. All right, and here I'm just showing them evaluate it at the upper limit minus the lower limit. Evaluate the lower limit, it's just going to give me all zeros on all my terms. And there we end up with 85.3 Newton seconds. All right, that's it. Okay, well, we were asked for the velocity, so it was one last step. We're going to go ahead and then say that change in momentum, of course, is equal to impulse, which means mv final equals impulse. This is the same as the last example in as far as that v initial is 0, so it doesn't show up. All right, and then that means that v final is just impulse over m. All right, and our impulse was 85.3 Newton seconds. So there we go, divide by our mass, and we end up with 105 meters per second. All right, so pretty fast rock, but not as fast as a golf ball. Okay, so what is the velocity of the rock at the moment that the force is at its maximum? Okay, oh, that's interesting because the force is varying. It turns out that what the force looks like is it looks something like this. Being a third order polynomial, that in between these particular values, it kind of has this shape, okay? And so then we're interested in that point at the top where the tangent line is horizontal because that will represent the maximum, okay? And so then what we're going to do is we're just going to take the derivative of force with respect to time and then find the 0 of that derivative in order to find the value of the maximum. This is a common approach in calculus. Now, if we wanted to confirm it's a local maximum, not a local minimum, we could do the second derivative test, or we could graph it to confirm. Okay? All right, so, and then you set the equal to 0 to actually find the value of t at f max. And we find that the value of t that corresponds to maximum force is 2.52 seconds. And so then we're just going to go ahead and find the impulse from impulse by integrating from 0 to 2.52 instead of the full 4 seconds, all right, because that will give us how much velocity the rock gained up until that point where the force is maximum, all right. And again, it's interesting, right, that we have to work up to that point because, of course, the rock started at rest, so we need to find out how fast it's going, which does require integration, all right. And so I'll just do the same approach, but at different limits here, and then I get 49.8. It should be less. That makes sense. And then we do the final step like we did in part A to find the velocity. So simply take the impulse divided by mass. And there we go. There's our numbers. And it's 61.1 meters per second. All right. Great. Which means it's almost like symmetric. It's like we almost have just as much speed up. Well, I guess we're six tenths of the way there. Okay. All right. Let's do another one. This is almost like a conceptual question, but it does have some numbers in it. So I decided to label it as an example. So what is the impulse provided by each of the forces shown in the graphs? So this is force as a function of time. Okay, well, it's interesting. Well, if impulse is the integral of force, or is force integrated over time, if impulse is force integrated over time, that means that graphically speaking, impulse is the area under a force versus time graph, isn't it? Well, there we go. All we're going to do is find the areas. All right, so there we go. Since this is force times time, the area under a graph of force versus time, all right, is impulse. And there we go. And so then we're just going to find the area. We're just split it up into triangles and rectangles. Okay, and that's all I'm doing here. These are the two triangles. This is the rectangle. So I get 120 Newton seconds. This is the impulse for A. For B, I get 100 because it's just the two triangles, or just one triangle really. All right, 1/2 base times height. All right, then we get a real simple rectangle for the third one. All right, and then for the last one, it's the same shape as A, but it's negative, and so it's just going to be negative 120 instead of positive, because impulse can be positive or negative. It is, after all, a vector. Okay, now let's do a concept question since there's no numbers in this one. A particle moves along an x-axis. Its momentum is graphed as a function of time. Rank the numbered regions according to the magnitude of the force acting on the particle, least to greatest. Well, here we have it, right? If we're doing graphical interpretations of calculus, and we have a definition like this, we have F equals dp over dt, okay, and then we likewise have that F equals the integral of J equals the integral of F dt, right? Then we can always have some graphical interpretation. And this one here is just going to be entirely based on the idea of the tangent line, just like this one was entirely based on the idea of the integral. And the tangent line, just to rewrite it, is just going to be that F is dp over dt, okay? Our axis is time, just like in the previous example. But now we're concerned with the tangent line. All right, since this is a kind of discontinuous curve here, right? Then we don't have to really think about approximating the tangent line. It's just these chunks, because in other words, the force remains constant for this whole region, and so there's a sudden abrupt change, and then constant force for a while, sudden abrupt change, constant force for a while, and so it's just the slope. All right. So that means if we're going to rank the forces, the steepest upward slope is the greatest force, and the steepest downward slope is the smallest force, because negative is smaller than positive. All right, so there we go. This is just showing where we get it from. So the force is the slope of the momentum versus time graph. And so then the simple ranking becomes, okay, see. I guess I left out the ranking. All right, so the ranking is going to be, we have, so if we're going from least to greatest, so least is 4, then we have 3, and then we have 2, and then we have 1. So from least to greatest is 4, 3, 2, 1. Okay? All right, great. Okay, so let's go ahead and look at this one here, example 6. I'll zoom in a bit on it. So a Pelton wheel, an interesting engineering idea, is a more effective version of the traditional water wheel. The Pelton wheel delivers force to cups attached to the spokes of the wheel by forcing the oncoming water to make a U-turn. This is different than a traditional water wheel. It just kind of stops the water, like in more of like a bucket, all right? Or maybe just pushes against a paddle, which doesn't stop the water even completely. If the water is delivered to the wheel at a mass flow rate of 65 kilograms per second, okay? So there's a mass flow rate like we saw in that last equation in our key equations. At a velocity of 28 meters per second, what is the force exerted on each cup of the wheel by the water? How much force is delivered by the water in using this Pelton wheel than would be delivered by the paddles of a traditional water wheel that just makes the water come to a complete stop, but doesn't change its direction, okay? So the approach here is that the force on the wheel is equal to the negative of the force on the water. That's just Newton's third law, okay? And that's going to be good because that's going to clearly set up, what force we're talking about. So then the force on the wheel is given by the equation that I gave you. It's the negative of the mass flow rate times the change in the velocity. And so then it's negative 6.5 kilograms per second, the mass flow rate. The final velocity of the water is negative 28. The initial velocity of the water is positive 28 because we're calling the positive direction this way. And that means that our delta V is negative 56, but that also means that since we have a negative times a negative, the force on the wheel is in the positive direction, which it should be, because the force should be in the same direction as the initial velocity, in the positive x direction. So 364 newtons, okay? All right, what about the traditional wheel? Well, the traditional wheel, same approach, but look at our V final. It's 0 instead of negative 28. That means there's a smaller change in momentum for the water that's not forced to turn around, thus there's a smaller force. So forcing something to turn around is a great way of getting more force delivered. Or sometimes forcing something to turn around is a bad thing because then you're delivering too much force, more force than something can handle. All right? So anyway, so in this case it is positive 182 newtons, the force on the wheel. And so then we see the difference is in fact just 182. We get double the force when we force the water to turn around. Okay? All right, so there you have it, our introduction to momentum. We'll be doing a lot more with momentum. We're going to see it in the context of collisions and explosions, and then collisions in 2 dimensions. Okay? All right, well, thank you so much for watching this lecture. I hope it was helpful.